Let's look at a variety of use cases for window functions. Welcome to this video on window functions. My name is Kevin Fiesel, and I'm the proprietor of Catalaxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. So far in this series, we have gained a better understanding of what a window function is, as well as the types of window functions available in SQL Server as of SQL Server 2022. In this video, we are going to take it a step further, and I'll demonstrate a variety of real-world use cases for window functions, including scenarios you might have run into during your database development work. I don't have any custom classroom material for this one, so let's just jump straight to the demo. Here we are in Visual Studio Code. In this video, we'll look at 8 use cases for window functions. There are plenty of others, but this should hopefully spur on some thoughts around how you might use them. The first example is something we commonly run into as database administrators. Somebody creates a table in SQL Server and doesn't put proper constraints on it, promising that, don't worry, the app will prevent duplicate entries. Well, 6 months later, it turns out the app isn't doing a great job of preventing duplicates, and the developer comes back in and asks if you can fix the data. It turns out the answer is yes, and here's how. I'll create a simple table that includes event dates and attendee counts. Then we'll insert 1 dozen entries. But oops, we ended up getting some duplicate entries in our table. We now have 19 total entries, but some of them are repeats, and our job is to remove those repeats. Now let's suppose that the simple business rule is we can only have 1 event per day. To do this, we can use the row number window function. We know that event date should be unique, so we'll make that the partition by column. Then I've decided to keep the first entry for a given date. This query is inside a common table expression for a reason that I'll get to soon, but let's first run the select statement and make sure our output looks reasonable. We can see 5 total entries for April 1st, 3 for April 8th, and 2 for April 29th. But here's the neat thing. If row num is equal to 1, we want to keep that row. If row num is anything other than 1, we can get rid of the row. Thus, our query to fix the problem starts with the same common table expression, but instead of a select operation, we delete from records where row num is greater than 1. That deletes 7 rows, which is exactly what I would have expected. And running this query, we get back the 12 original records. Not bad. The next scenario I want to discuss is something we've already covered, but it is important enough that it's worth bringing up again, and that is calculating running totals. Running totals are very common in business applications, as people want to see how numbers have changed over time. A running total involves the sum aggregate function. In this simple scenario, I don't have anything to partition the data over, so we'll have one contiguous window crossing the entire data. We do need to sort the data, and so I'll do that by event date. And I do need to make sure that I'm using rows as my frame operator rather than range, as we don't want to deal with incorrect behavior if there are multiple entries with the same date. Running this query, the results are exactly what we would expect. We start with 150 attendees, add 165 to get 315, and so on through the list until we reach 1,925 attendees at the end of the set. Related to running totals, we have moving averages. People like using the mean of a set to smooth out values and reduce the impact of one-off outliers. But if you're dealing with time series data and the series gets too long, the mean may obscure more than it clarifies. For that reason, a common practice is to look at a short-term smoothed average and maintain that over time. For example, we might want a 6-month moving average if we have decades worth of monthly data. Or because we have weekly data in this data set, we could look at a 3-week moving average. But why do this rather than report the individual values? Well, let me describe a scenario. Let's suppose we're looking for advertisers for the events that we are hosting. Advertisers want to get a good feeling for how much impact the event has. How many people will see us? How many potential leads does that generate? And so on. If I had an abnormally high or low number of attendees the prior week, that might give the wrong impression to the vendor and could either cause us to miss out on an opportunity or give them a false sense of what is reasonable. So instead, we're going to smooth things out a bit and calculate a 3-week moving average of attendee counts. And it turns out that doing this is very easy in SQL Server. In this query, I use the average aggregate window function. Once again, I don't have any need to partition this particular sample data set, though I do need to sort it by event date to make sense of the time series data. I want to average out the 2 weeks prior to the current week, in addition to the current week, and that will give me my 3-week moving average. Note once again that we use rows rather than range. For a mean, it's probably not as critical for us as a summation, but it's still good to have a clear picture in your mind of which frame type you need for your specific problem. Now let's run the query. If you think carefully about the problem definition, you might have been concerned about the first 2 weeks in our data set, as we didn't have any records from prior to April 1st. In that case, if we filled those values with zeros, that would drag down our average and be really confusing. So instead, SQL Server ignores those missing records, and thus the average as of April 1st is just the record on April 1st. So it's 150 divided by 1, or 150. Then the average for April 8th is the quantity 150 plus 165, quantity divided by 2. That is 157.5, but because we are working with integers here, we lop off the decimal portion and return 157 attendees. It's only the 3rd week in which we have a full trio of records for averaging. But from there, in week 4, we drop off our first data point and only care about weeks 2, 3, and 4 together. One quick note before I move on. I've been talking about this as 3 weeks, but technically it's 3 rows, and it's not 3 weeks. That's because SQL Server does not have the concept of date interval calculations in window functions like you might find in Postgres. Our data set is a series of contiguous weeks, so it doesn't really matter which way we frame it mentally. But if you do have gaps in the data, you will need to take that into consideration, as your moving average would no longer be a guarantee of 3 contiguous weeks, but rather this week and the 2 prior weeks that contain data. The next thing I'll show off is how to calculate percent of a total. We've seen running totals and we've seen grand totals. Armed with those 2 calculations, we can determine percentages in 2 ways. The first way is on line 110, where we calculate one row's contribution to the total in terms of percentage. We have the number of attendees, which I multiply by 1.0 in order to coerce this integer into a decimal number, and then divide by the grand total, the sum of attendees over the default window. Then on lines 111 through 115, we calculate a cumulative percentage, which is the running total divided by the grand total. If I execute this query, we see that there were 1,925 attendees in total, noting that a person who attends 4 different events counts as 4 entries toward the total. The first event had 150 attendees, and 150 divided into 1,925 is approximately 7.8%, which is what our percent of the total and cumulative percent values show. Then the second row has 165, which is approximately 8.6% of the total. And if you add those 2 together, you get the cumulative percentage of 16.36%. This goes on until we get to a cumulative percentage of 100, so everything looks good. These sorts of aggregation calculations are by no means the only useful thing we can do with window functions. In this next example, I'll show how we can get the latest orders for each customer. I'll focus on the customers whose names do not include the word toys in them, so we can cut out the Tailspin Toys purchases from here. Then I'd like to find the 5 latest orders for each customer. I'll start with a common table expression that I'll call customers, and this will retrieve the list of valid customers. This common table expression is not strictly necessary, but I wanted to keep the demo code as easy to understand as I can make it. The next common table expression covers invoices. We join the invoices table to the customers table, and we generate a row number for each customer ID ordered by invoice date descending. That way, the invoice with the latest date will have a row value of 1, the second latest date will have a row number of 2, and so on. If there are ties, we arbitrarily assign unique and monotonically increasing values for each row number. Finally, in the main query, we bring back in the customers table and include any invoices where row num is less than or equal to 5. Running this query, we get a total of 1,665 rows back and can see the latest invoices for each customer. Now, if you watched my series on the apply operator, you'll know that this query form requires one scan of the invoices table. This is the best option if we are retrieving at least 20% or so of the total number of records from this table, and it could be the best option if we are retrieving at least roughly 0.5% of data from this table. Otherwise, using something like the apply operator to force a nested loops join will become more efficient. If you're interested in those demonstrations, I'll include a link to the Apply Yourself series, and you can check that out there. But do keep in mind that this can be a very efficient way of solving this sort of problem, assuming that you want to return a significant percentage of the total number of invoices. Next up, I'd like to show you how we can find the distinct order count over time. To do so, we'll start with another common table expression in which we'll scan the orders table. I'll select the order date and use the case expression, returning the customer ID if row number is equal to 1. This is a fairly clever way of avoiding a second common table expression in which we filter the results of records where the row number is equal to 1. Instead, in our main query, we have order date and a second window function. This time, it's an aggregate window function that gets the count of customer IDs sorted by order date. Recall that the default frame for this aggregate function with an order by clause will be range between unbounded preceding and current row, so we take care of cases in which multiple customers have their first order on the same day. Running this query, we see that there were 43 customers whose first order was on January 1st of 2013. Another 43 customers had their first order on January 2nd, getting us to 86. This number increases fairly steadily for the first few weeks, but then it starts to slack off as we get into February and March of 2013, where we have multiple days with the same number of customers. And as we move forward, the numbers slow down even further, helping us tell a story about our marketing efforts and total addressable market. Something really neat that is now available in SQL Server 2022 and later is the idea of last observation carried forward. To demonstrate this capability, I'm going to put together a slightly dumb query based on our event table demonstration. I'll start by calculating the running total of attendees across my events. We've seen this formulation already, and the only thing that I'm doing differently is I'm slamming it into a common table expression. Then, after that, I'm going to use the generate series function to build out 85 rows. I'll use the date add function to start my range on April 1st of 2021, and that will give me back one row per day. Running the contents of this common table expression, you can see the results are pretty straightforward and they end in June of 2021. If you have a calendar table, you can avoid this bit, but that's a recommendation for a different video. Now, what I want to do is show the running total by day, and that's what the main query does. We have our dates and left join to events. The event has a running total, and if I run the entire query, I see a bit of a problem. We have 150 attendees on April 1st, but then we have null until April 8th when the number goes to 315. This isn't the behavior we want to see, though. We want to see 150 for the running total on April 2nd, on April 3rd, and so on until it changes on the 8th. How can we do this? Well, I'm glad I asked, because if you're using SQL Server 2022 or later, it turns out that there is an easy way to implement last observation carried forward. Scrolling down to this next query, I have the same pair of common table expressions as before. But now, instead of taking running total as is, I slap it in an isNull function. Inside of the isNull function, I'll use the running total calculation, if I have one. If not, I'll use the lag function and the new ignore nulls clause. This was introduced in 2022, and what it does is, it does not consider any nulls with a running total of null in calculating the number of rows to move for our lag or lead operations. If I use, for example, lag of running total and look 3 rows back, and if I include ignore nulls in my lag function invocation, it would keep going back in the data set until it found the third row with something other than null for the running total. With the default lag definition, I know that it will look one row back, and that's exactly what I want for last observation carried forward. Let's run this query and see what we get. Now I can see 150 as my running total until we have the next event. At that point, the running total becomes 315 and stays that way until the 15th when we have our next event. This continues through the data set, and I no longer have nulls on days without events. Last observation carried forward is an extremely useful technique in data science tasks, and it's nice to see an easy implementation of it in versions of SQL Server 2022 and later. I would also recommend being on compatibility level 160 or later, just to be sure. The final example I'll cover is to turn start date and end date into an event system. I want to give credit to Itzik Ben-Gan, from whom I learned about this technique. We are going to answer the question, for each customer, what is the largest number of orders en route at any given time? Let's first take a peek at what's available in the orders table, just to familiarize ourselves with it. In this table, we can see the customer ID as well as a couple of dates. There are 2 dates that can help us answer our question. We'll use the order date as the start point and the expected delivery date as the end point, as we don't have exact order fulfillment dates, but these should serve the purpose well enough. I'll start with a common table expression called start-stop points. In it, we have 2 separate queries combined together using the union all operator. The first query gives us the customer ID, the order date, a hard-coded 1 to indicate that this is a starting point, and the row number by customer ID, ordered by order date, and the order ID as the start ordinal. Although row number does generate a monotonically increasing value for each record, and there is no possibility of a tie, I do still need a guaranteed ordering to get consistent results. If I do not include the order ID here in the start ordinal column, each run will give me different values because there can be multiple orders on the same date for the same customer. With that in mind, I can run this query and we'll see 860,773 results in no particular order because I did not have an order by clause in my select query. The second query gives us the expected delivery date, 0 as the starting point, and null as the start ordinal. Running this, we will again have 860,773 records. So we have 1 record for the start, 1 record for the end in this common table expression, giving us a total of 1,721,546 rows if you do the math. In this second common table expression, which I'm calling start-stop order, I want to organize these results such that we have all events, whether order or delivery, show up in contiguous order. To do this, I'll use row number again. Partitioning by customer ID, I want to sort row number by the time, whether this is a starting point, and the order ID. The idea behind this ordering is that we process the delivered records prior to adding the new order records. That way, we don't artificially inflate the number of records currently out for delivery. If I had 10 orders out for delivery and I received 5 of them today and also added 3 new orders for delivery, the end result will be 10 minus 5 plus 3, or 8, rather than 10 plus 3 being 13, and then having the 5 disappear the next day or something like that. This gives me the column start or end ordinal, and I can compare that to the start ordinal from before, which only includes new order dates and not their delivery dates. My main query drives from the start-stop order common table expression and filters where is starting point is set to 1. So we only look at the starting records. Then we get the customer ID and calculate the number of concurrent orders. This does not use a window function, but instead is a simple aggregate. We take the start ordinal, multiply it by 2, and then subtract the start or end ordinal to get back the max number of concurrent orders. The idea is that if I only have 1 order out for delivery at a time, my start ordinal will be exactly half of my start or end ordinal, and let me demonstrate why. The first order will have a start ordinal of 1. Then it eventually gets delivered. So in my start or end ordinal column, I'll have a row of 1 for the start and a row of 2 for the end. Well, 1 times 2 equals 2. 2 minus the starting point of 1 equals 1. So we had 1 order out. The next order will have a start ordinal of 2 and its equivalent start or end ordinal value is 3. It's 3 because we had 1 representing the first order's departure, 2 represented the first order's arrival. So 3 is the second order's departure. Multiply the start ordinal's value of 2 by 2, and you get 4. 4 minus 3 is 1. So again, we only have 1 order out at this time. But now let's suppose that I have 2 orders go out on the same date, or at least where the second order goes out before the first order arrives. I'll call these orders 3 and 4. Their start or end ordinal values will be 5 and 6, respectively. So order 3 has a start or end ordinal value of 5. Order 4 has a start or end ordinal value of 6. 4 times 2 is 8. 8 minus 6 is 2. So I have 2 orders out at once. That's the logic behind how this all works. And when I run the full query, I can see that we have 4 customers with a maximum of 14 concurrent orders at some point in their history, and another 2 had 13 concurrent orders at some point in time. This approach is a really clever way of converting classic start and end dates into an event system, allowing you to track the frequency of concurrent events. This can also help in scenarios like figuring out how many cashiers to have on a given shift based on the amount of customer traffic in a store. And I've even used it in a prior job when a development team found a bug that only popped up when there is a certain level of concurrency in their system. I was able to help them pinpoint the time frames that may have been affected by this bug. Thus, they were able to limit the scope of their potential fixes and get the actual data points that were broken fixed. That's going to do it for this discussion of use cases for window functions. This was by no means an exhaustive demonstration of everything you can do with window functions, but I did want to demonstrate in this video that you can solve a variety of relevant business problems with them. In the next video, we'll take a step back and get a better understanding of how window functions are not perfect, and there are limitations you'll want to know about. We'll have links and show notes in the description below. And until we see each other in the next video, take care.